Hello everyone. In this video we're going to look at solving equations containing radical expressions. As usual, we'll start with some simple cases and we'll work our way to more complex ones. And one thing that's extremely important to note is that with equations containing radicals where the index is even, such as in this case where we know it's 2 for the square root or the fourth root, etc. These are mandatory check problems because in the course of solving them, we're going to be modifying the equations in a non-basic way, meaning involving operations other than just adding to both sides, subtracting, multiplying, or dividing from both sides. And that means sometimes we'll get solutions for the modified equations that won't work for the original ones. So when the index is even, we definitely have to check these. When it's odd, it's also a good idea to check, but the ones that are even are mandatory check problems, just so you know as we proceed. So starting with this first equation on the left, as you can see, we have the square root of w equals 5. Now, what's going to be really helping us here is this property that we learned earlier, which was, let's see, this pen is not cooperating. Here we go. The nth root of any number, as long as it turns out to be a real number, raised to the power of n, just gives us x. Now, for the case of square root, for example, if you take the square root of any number and square it, you get the number itself. For the case of cube root, of course, if you want to get x, you'll have to cube it. So we're going to be using this property very heavily. So we'll start off right away on the left side here. We notice that we have the square root of w and we're trying to solve for w. So we're going to go ahead and square both sides like that. So we end up with w equals 25. That's an even index, so we have to check it. And when we plug in 25, we want to know if the square root of that is going to be 5. And of course, we know that the positive square root of 25 is 5. So we get 5 equals 5, and it checks out. So we can write our solution set, and it's going to contain 25 in it. Now, this next example will demonstrate why we must check these even index problems, because if we were to approach this problem in a standard way like this, we would run into problems, as you'll see. But of course, looking at a problem like this one, if you're alert enough, you should realize right away, how can there be a real number whose square root is -5? There is no such real number. So if you're alert enough with a problem like this, you could say no solution right away. But let's say we were in autopilot mode and we just went through the motions and we just went ahead and squared both sides. So we would end up with this scenario, and we would get w equals 25. But then, as long as we checked it, we would realize that when we ask whether the square root of 25 equals -5, we would find out that it in fact is not, because this is the positive or principal square root of 25, which, as you know, is 5, and that is not equal to -5. So this one fails, and therefore the only potential solution turned out not to be one. So in this case, we say the solution set is the null set or the empty set. We can write it using that symbol, or we can just put a set notation using braces and just put nothing inside it. That has the same meaning as this. Just don't use them together. Don't put this inside that, and you should be fine. Now, you can see why it's so important to check. Of course, this was a super simple example, but it gets the point across as to why we need to check these. Because notice, squaring both sides of an equation is not a simple operation, is not a basic operation, such as adding to both sides, subtracting from both sides, multiplying both sides by a number, or dividing both sides by a number. It dramatically changes the original equation so that it may end up having solutions which do not work for the original equation. So make sure you check. All right. So of course, in this next one, we can see there's a square root, but there's also a constant here. So before we square both sides, we're going to go ahead and get the square root term by itself. So we're going to get square root of z plus 9 equals 1. Now we can go ahead and square both sides. So we end up with z plus 9 equals 1. And z is equal to 1 minus 9. So z equals negative 8. We quickly check it, and we realize the square root of negative 8 plus 9 is in fact equal to 1. Well, since we're checking, we'll go ahead and put a question mark above that equal sign, but in the next step we realize we get square root of 1 equals 1, and the square root of 1 is 1. I mean, ideally your check should continue with question marks until you get to the identity like this, or a contradiction like this. Once you reach the identity, of course, you know that the value that you found is indeed a solution, and you go ahead and put it inside a solution set. So you say the solution set contains negative 8. Be careful, because sometimes what some people make a mistake about is that they put the last step of their check as the solution. No, the solution is actually the value of z that makes the original equation true, and as we know, that's negative 8. So these are very simple examples, but make sure you understand them, please, before we proceed. All right, so we'll continue our quest here with these next few problems. As always, please try to do them on your own first, pause the video, and then come to see if you did them correctly for maximum benefit. All right, welcome back. So here we can see that we need to isolate the square root term. So to do so, I'll just go ahead and move the negative 11 to the other side by adding 11 to both sides. So we end up with negative 9 plus 11 equals square root of 3k plus 1. Now we know that negative 9 plus 11 is 2, so we get 2 is equal to square root of 3k plus 1. Now we're ready to go ahead and square both sides. Notice we do not square both sides until we have isolated the square root term. That's very important. So we get 2 squared equals square root of 3k plus 1 squared, and we get 4 equals 3k plus 1. Now we can simply solve for k, so we get 3k equals 4 minus 1, so 3k equals 3, and finally we get k equals 1. So we're going to check it. So we just plug this into the original equation as it was with no modification. So we get negative 9, and we're trying to see if that equals the square root of 3 times 1 plus 1 minus 11. So next line will be negative 9. We're still checking, so we keep the question mark. Of course, we know this is 3 plus 1, which is 4, and the square root of 4 is 2. So we get 2 minus 11. Now we can drop the question mark because -9 does indeed equal -9. So that checks out, and now we can write down our solution set, which contains k equals 1. So remember, you don't need to put the k or the equals, you just put the numerical value of the solution in the solution set. Okay, so moving on to this middle problem, notice we have the square root of 2b minus 1, and if we isolate it, we end up with -3 on the other side. It doesn't matter what the expression in here is. If you're alert enough, again, you can go ahead and say no solution at this point because there is no real number whose square root is a negative number. Or if you were not paying attention and you just went through the motions, you would end up with something like this. You would end up with the square root of 2b minus 1 squared equals -3 squared. And 2b minus 1 equals 9. So 2b equals 10. And b equals 5. However, when you check it, you notice that the square root of 2 times 5 minus 1 plus 3, checking to see if that's equal to 0, may not actually end up so, because here we notice we get the square root of 10 minus 1, which is 9, and the square root of 9 is 3. So we get 3 plus 3. We're checking to see if that's equal to 0. Of course, 6 equals 0 is a contradiction. Therefore, the only number that could have been a solution, namely 5, appeared not to be. Not surprising to us because we had already figured out in the beginning that there would be no such real number. So at this time, we say the solution set is empty. We can write it in both of those manners. All right, so moving to this last problem on this page, we notice that we have x equals the square root of x squared plus 9x minus 36. Now, this square root is already isolated on one side, so we can go ahead and square both sides. So we end up with x squared equals the square root of x squared plus 9x minus 36 squared. So then we get x squared equals, of course, it doesn't matter what the radicand is. As long as you're taking a square root and squaring it, you always get the radicand as it was. So here we end up with x squared plus 9x minus 36. Now we notice that we have the exact same term on two sides of an equation, and of course we know what that means. That means we can just subtract it off and they cancel out. Of course, don't forget that that leaves a 0 on this side. It doesn't leave nothingness, it leaves 0. And 0 is a perfectly significant number like any other number. So next line will need 0 on the left side. A mistake some students make is they leave that out and they just write 9x minus 36 like that. And of course, 9x minus 36 equals blank is not an equation. You would have to have two expressions on either sides of the equal sign for it to be an equation. So you must write 0. And now we can just solve this simple equation. So we get 9x equals 36. So x equals 4. Now we check it. And we want to know if 4 is equal to the square root of, we're plugging in 4 every place we see x. So 4 squared plus 9 times 4 minus 36. So we want to know if 4 is equal to the square root of 16 plus 36 minus 36. These two, of course, cancel out, and we end up with 4, and we're trying to see if that's equal to the square root of 16. And of course, the positive square root of 16 is 4. So we get 4 equals 4, and this equation works out with that number. So the solution set indeed contains the number 4. And that's how we handle a problem like that. So please make sure you can handle these on your own by copying them down and working them out. Make sure you get the right answers before you continue. All right, so we notice for the first time that we have some equations that contain 2 square roots in them. Now, as long as those square roots have variables in the radicand, what we want to do is make sure that we get no more than 1 square root per side. That makes it much easier to solve. So we can, however, proceed just like before. Notice that right here we're ready to go ahead and square both sides. So that's what we'll do. And we end up with the square root of 3a plus 1 squared equals square root of 5a minus 9 squared. Now we know that the square root of any radicand squared just gives us the radicand. So 3a plus 1 equals 5a minus 9. And we simply need to solve that simple linear equation. So let's go ahead and move the 3a to the right side, and it becomes minus 3a. And we'll keep the 1 on the left side and bring the negative 9 to the left side, which becomes plus 9. So we end up with 10 equals 2a, so a equals 5. I will go ahead and check it because it has an even index, and even index problems containing radicals, equations containing radicals, are mandatory check problems. So we get square root of 3 times 5 plus 1, and we want to know if that's equal to the square root of 5 times 5 minus 9. On the left side, we get the square root of 16. And on the right side, we get the square root of 25 minus 9, which is also 16. And that's actually where we can go ahead and take out the question mark, because that right there is an identity. We don't need to go any further. And if you wanted to, go ahead and say 4 equals 4, that's fine, but you didn't have to, because you had the positive square root of 16, and those two are already creating an identity. So we could have stopped in the previous step. And but you know, if you want to go till we get to the whole number, that's fine. So that it checks out, and we can write the solution set as the set containing 5. Be very careful not to put 4 in there. All right, definitely try to do the next couple on your own before you come back to see the results. All right, so assuming you're back from your attempts, here we notice that we have 2 square roots on one side. So we're going to go ahead and move one of them to the other side. I'll go ahead and move the negative 3 radical h plus 7 to the other side. So we get square root of 3 minus 11h equals 3 radical h plus 7. And now we can go ahead and square both sides. There's no need to try to get rid of this 3 or anything like that, because we can go ahead and square it. And if you try to get rid of it, you would just end up with a 1/3 over here anyway, so it doesn't do us any good to do that. So we'll just go ahead and square both sides. So we have the square root of 3 minus 11h squared is equal to 3 times the square root of h plus 7 squared. Now on the left side, we're just going to get 3 minus 11h. And on the right side, of course, we need to square the 3 as well. So make sure you don't forget that. That'll give us 9. And when we square the square root of h plus 7, we just get h plus 7. So now we have 3 minus 11h equals 9h plus 63. Let's go ahead and move the h terms to the right side. So we have 9h, we bring over the negative 11h, it becomes plus 11h. On the left side, we keep the 3 and move over the 63 to become negative 63. So we end up with negative 60 is equal to 20h. So we have h is equal to negative 3. Of course, we'll want to check that. So we have square root of 3 minus 11 times negative 3. We're trying to see if that's equal to 3 times the square root of negative 3 plus 7. Since we're checking, we need the question mark. So we have the square root of, that becomes 3 plus 33, right? So that's 36. And we want to know if that's equal to 3 times the square root of negative 3 plus 7 is 4. So we get square root of 4. Now we know that the square root of 36 is 6, and we're trying to see if that's equal to 3 times the square root of 4, which is 2. So we end up with 6 equals 6, which is good news because that means all our work paid off and we had a solution, which is negative 3. So we can write our solution set to contain negative 3. All right, so very simple as you can see so far. You just have to be careful, make sure you check. All right, let's go ahead and try the last one on the right. And okay, so we're going to get no more than 1 square root per side. So we're going to go ahead and do that whenever that's possible. So we get negative 2 square root of p plus h. p plus 4, I mean. So now we go ahead and square both sides. So let me be a little bit lazy here and just go ahead and do this to save us some time and space. Valuable commodities indeed. So we end up with 2p minus 1 is equal to, when we square negative 2, we get 4. And when we square the square root of p plus 4, we get p plus 4. I do hope you noticed something a little bit subtler in the previous step. Notice we had ended up with square root of 2p minus 1 equals negative 2 radical p plus 4. Now we know that the square root of 2p minus 1 is going to be non-negative, and we know that this needs to be non-negative. So we're trying to find a situation where a non-negative number equals negative 2 times another non-negative number, and you know that's impossible. So you know that the only possible solution may be 0. But if that doesn't happen to be the number that's going to work, I mean, a number that makes this and this 0. If that happens, then maybe we can get a solution out of this. But otherwise, it's unlikely that we're going to find a solution here. So Most of the eagle-eyed among you might have detected that already. So let's keep going. So we have 2p minus 1 equals 4p plus 16. And now we go ahead and move the 2p to the right side, so we get 4p minus 2p. On the left side we have -1 and bring the -16 over. So we end up with -17 equals 2p. Therefore p equals -17 over 2. So now when we go ahead and evaluate, we end up with, or check is basically what we mean. We go ahead and plug in, so we get square root of 2 times -17 over 2 minus 1. We're trying to see if that's equal to -2 times the square root of -17 over 2 plus 4. And right here we have the square root of -17 minus 1 equals, I'm just going to put dot dot dot, because if you notice right here, that's not a real number. So that's pretty much where we can stop and realize this is not going to work out. So at this point we can safely go ahead and say what we had already detected might be happening, and we can say solution set is empty. All right, so these are, I hope you've realized by now, these are definitely mandatory check problems. You must check them, otherwise you may plug something like this into for an answer and get it wrong, and then that could bring frustration. So make sure you're always checking when the index is even, and of course when there is no index written, you know it's 2, which is of course even. So go ahead and make sure you can try this and do this on your own before we proceed. Okay, so in this next set of problems, we can see that we have a square root here. We also have a binomial on this side, so we need to be really careful with these, because yes, we're going to go ahead and square both sides. And get this scenario. And one of the most common mistakes in mathematics is when a student sees this expression, they make the mistake of writing x squared minus 36, which is of course not the case. So let's be very careful not to ever make that mistake. Of course, the reason the student makes that mistake is because if you had x times -6, for example, being squared, that would be okay. You would get 36x squared. But here, it's a subtraction, and when that happens, we know that we need to expand this and FOIL it. So now you can either use a formula such as f minus l squared equals f squared minus 2fl plus l squared, or probably the safest thing, just quickly multiply it out in one of these nice tables. You have x minus 6, x minus 6, and you just multiply it out like a times table. So you have x squared minus 6x, notice, multiplying x here and then here. Now you're going to multiply here, so you're going to get -6x, and then you'll multiply here, so you get plus 36, and these can be combined, so we get the square root of x squared, we know is just x, and on the other side we have x squared minus 12x plus 36, which of course you could have gotten from that formula too. So you get x squared minus 12x plus 36. So we can see how badly incorrect x squared minus 36 is. For one thing, it completely misses the middle term. For another thing, it's not going to end up being minus 36 anyway. If you notice, it becomes plus 36. So make sure you don't make that very, very unfortunately common error. All right, so now we notice that this time we don't simply have a linear equation on our hands, we have a quadratic equation. Remember that for higher order equations, whether it's quadratic, third degree, or higher, we don't take the linear approach, which is to separate the variables and the constants. In fact, what we need to do is we need to get all terms on one side, and then we're going to factor, and then we'll apply the zero factor property. So here we're going to go ahead and move the x to the other side, so we get 0 left on this side. Extremely important to write your 0, otherwise you've demoted your equation down to the level of an expression. So you have to write the 0. And on the right side we have x squared minus 12x plus 36, and the x that's moving over, so minus x. Remember, change sides, change signs. So we get 0 equals x squared minus 13x plus 36. And here we're going to be factoring this quadratic trinomial. And if you remember from previous chapters, that's easy enough. We want two expressions here whose product is x squared, two expressions here whose product is positive 36, and at last we have to make sure the inner product and the outer product add up to the middle term. It's important to check all three of those things to get this factored correctly. So this is simple enough. You know that x and 4 and 9 should work, and since we want the inner product and the outer product to combine to give us negative 13x, we realize they both need to be negative. So this is negative and this is negative. So let me go ahead and erase that now. All right, so now we apply, so then we're going to say, therefore, by the zero factor property, let me remind you what that said. It said if a times b equals 0, that implies either a is 0 or b is 0. And remember, in mathematics, that's an inclusive or, unless specified otherwise. That means it could be this or that or both. When you use or in regular English, it's usually exclusive. When you say, I'm going to go to the movies tonight or to the live theater, you usually don't mean I'm going to do one or the other or both. You mean I'm either going to do this or that, but not both. That's what's called an exclusive or. But when you see or used in this manner in mathematics, that's an inclusive or. All right. So now we use the zero factor property. This is playing the role of a here, and x minus 9 is playing the role of b. So we get either x minus 4 equals 0 or x minus 9 equals 0. Even though or is not logically equivalent to a comma, we a lot of times go ahead and just use a comma anyway. It's technically incorrect, but we do it all the time anyway. So we get x equals 4 or x equals 9. Now we have two solutions that we need to check. So I'm going to go ahead and get rid of some of this preliminary stuff that we had here, so we have some room to check. Okay, so now we're going to check x equals 4. That means we're going to plug in 4 wherever we see x in the original equation. Try to always leave your original equation alone so that when you go back to check, you don't plug into the wrong thing. So try not to modify that by putting squares around it or anything like that. Go to the next step. It's a little bit of work, but it pays off. So we're going to plug in 4, so we get square root of 4, and we're trying to see if that's equal to 4 minus 6. Now we know that the square root of 4 is 2, and on this side we have negative 2, and of course that's a contradiction. So therefore this one did not work. So if we want to be a little bit more technical, we replace the sad face with false, because that turned out not to become true. Now we're going to go ahead and plug in and check x equals 9. See if we can do better there. So we have square root of 9. Remember, we're plugging into the original equation. We're trying to see if that's equal to 9 minus 6. Now square root of 9 is 3, and of course that equals 3. So this one became true, so this one is a solution. So even though it looked like we may have two solutions, one was not working, so the only solution that works is 9. So now we're going to write our solution set, and we're going to be careful to only put 9 in there. And that is how we do that kind of problem. So as far as a little bit of terminology, this x equals 4, which ended up not working, we call an extraneous solution. So the only actual solution is 9. All right, so moving on to the next problem. Okay, so we can go ahead and square both sides once again. Definitely try it on your own before you come back to watch. Pause the video and try it. You can do this. All right, so assuming you're back, we're going to go ahead and square both sides. Remember, leave the original equation alone. Equals 5 radical m squared. So now we're going to square m plus 4. So m plus 4, m plus 4. We definitely are not just going to write m squared plus 16. We know better than that, right? So here we get plus 4m, another plus 4m, just like a times table, and then plus 16. And what's nice about this method is that the like terms line up just like that. So we get m squared plus 8m plus 16 on the left side of the equation. On the right side, we know we need to square the 5. That's going to give us 25. And we know that the square root of m squared is just going to be m. So we get 25m. We have ourselves a quadratic situation again. So we're going to go ahead and move all terms to the one side. In this case, left side is easier. So we get m squared plus 8m plus 16 minus 25m equals 0. So we get m squared minus 17m plus 16 is equal to 0. Now we need to factor that. Again, that's not a very difficult factoring problem, so we end up with m and m, and I think that's easy to see that negative 16 and negative 1 will work. Now make sure you check the fact that, notice the first term here times the first term here gives you the first term in the trinomial. The last term here times the last term here gives us the last term in the trinomial. Negative times negative is positive. The inner product is negative 16m, and the outer product is negative 1m, and they combine to give us negative 17m. You always want to do that 3-step check, even if you just do it in your head, to make sure you factored it correctly. Now we're going to go ahead and apply the zero factor property, which says either m minus 16 equals 0 or m minus 1 equals 0. So we get m equals 16 or m equals 1. Now we need to check both because this is an even index problem. So we'll check m equals 16 first. So we get 16 plus 4. We're trying to see if that's equal to 5 times radical 16. And next line will be 20. We want to know if it's 5 times 4. And of course, now we can drop the question mark because 20 does equal to 20. So this one became true. It works. Now we're going to go ahead and check m equals 1. So we get 1 plus 4. And we're trying to see if that's the same as, always go to the original equation, 5 times the square root of 1. On the left side we have 5, and on the right side we have 5 times square root of 1, which is 1, and of course that's 5. So that was a quick check, and it works out too. So this time we actually have two solutions. They're both going to work. So we're going to write our solution set, and even though these kinds of sets for the solution set that we use are not ordered sets, you can put 16 comma 1. It's kind of nice to go ahead and put them in ascending order. That way all our answers will look the same. So we'll just go 1 comma 16 and we close the set. Also notice it's extremely important that you don't mistakenly put parentheses around those two numbers, because otherwise the system will interpret that as one solution, or whoever is grading your paper or observing your work. So make sure you do not use parentheses. Here you want everyone who is seeing this solution to realize that there are two separate solutions for the same variable. When you use parentheses, that means you're saying that the solution is one ordered pair. So you only do that when we deal with systems of equations with more than one variable. So no parentheses. All right, so again, make sure you can do these on your own without looking before we proceed. Okay, so for this next problem, we notice that we have more than one square root in the problem with radicals in the radicand position. So we'll go ahead and move this one to the other side so that we end up with only one square root on each side, because that's how these become much simpler to solve. And so we'll end up with square root of 3x plus 10 is equal to 2 plus the square root of 2x. Now we're ready to go ahead and square both sides. It's definitely a great idea to try to see if you can do it on your own before you continue. Okay, and now on the left side we have 3x plus 10. And on the right side, we know that we need to be careful because that's a sum being squared. So this time, to give you different kinds of practice, I would like us to go ahead and use this formula. F plus L squared equals F squared plus 2FL plus L squared. So here, the f that we're going to use is going to be 2, and the L we're going to use is going to be the square root of 2x. So we're going to apply this formula to this f and this L. So if you notice, we end up with f squared, which is 2 squared, which is 4, plus 2 times f, which is 2, times L, which is the square root of 2x, plus L squared, which is going to be the square root of 2x squared, so therefore just 2x. And now we have 3x plus 10 equals 4 plus 4 radical 2x plus 2x. Now we notice that, yeah, we've finished with simplifying the left side and the right side, and we still have a radical left. So we're not finished with squaring in this problem. We're going to go ahead and isolate this radical again, this radical term, and then we're going to square again to get rid of it. So let's go ahead and move everything else to this side. So we have 3x plus 10. We'll bring the 4 over, it'll become negative 4. We'll bring the 2x over, and it'll become negative 2x. And on the other side, we have 4 radical 2x. So the left side, when we combine 3x and negative 2x, gives us x. And when we combine 10 and negative 4, gives us plus 6. And on the right side, we have 4 radical 2x. No need to try to get rid of that 4 because that's going to create fractions. We'll just go ahead and square with the 4. So now we're ready to go ahead and square both sides again. And this time we'll be able to get rid of all radicals. So on the left side again, this time we're going to apply the f plus L squared formula, but this time we're going to use f equals x and L equals 6. So we end up with x squared plus 2 times 6 times x, which is going to be 12x, plus 6 squared, which is 36. And on the right side, when we square the 4, we get 16. And when we square the square root of 2x, we'll just get 2x. So times 2x. Okay, so we have x squared plus 12x plus 36 is equal to 32x. So we have a quadratic situation again, so we're going to go ahead and move all terms to one side and set it equal to 0. So x squared plus 12x plus 36 minus 32x equals 0. We can combine the 12x and negative 32x to get negative 20x. So we get x squared plus 12x, minus 20x plus 36 equals 0. So now we need to factor this. Now remember, this coefficient here is 1. So we had a nice trick for those. We kind of make a big X and we look for two numbers whose product is this last number, positive 36, and whose sum is the coefficient of the middle term, which is negative 20. Now, if you can do that in your head, that's fine. If you need some help with that, go ahead and find the prime factorization of 36, which, as you know, starts with 2, gives us 18, 2 again gives us 9, 3 will give us 3, and then 3 will give us 1. So we can see, for example, 4 times 9, or 12 times 3, or 2 times that, which is what? 18. And that's going to be the one that's going to do it, because we want to be able to combine and get 20. So of course, since we want two numbers whose product is positive but whose sum is negative, they'll both need to be negative. So here we're going to need negative 18 and negative 2. Notice when you multiply those two, you get positive 36. When you combine them, you get negative 20. So those are going to be the numbers that are going to do the trick. Let me continue here. So I get x minus 18 times x minus 2 is equal to 0. So we get x minus 18 equals 0, or x minus 2 equals 0. That, of course, by the zero factor property. So finally, as far as x values, we get x equals 18 or x equals 2. Now we just need to check both of those and see which ones work out. So here we're going to plug in 18 into the original equation for x. So we get square root of 3 times 18 plus 10 minus square root of 2 times 18, and we're trying to see if that equals 2. Therefore the question mark, because we're not asserting, we're checking. So we get square root of 54 plus 10, which is 64, minus the square root of 2 times 18, which is 36, and we're trying to see if that equals 2. Square root of 64 we know is 8, minus square root of 36, which we know is 6, and we're trying to see if that difference is equal to 2. And of course 8 minus 6 is 2, so we get 2 equals 2, which is a true statement. So that means 18 satisfied the original equation, so it's a solution. Now we'll check 2, so we're going to plug in 2 into the original equation for x. So we get 3 times 2 plus 10 minus square root of 2 times 2, and of course the square root on the first radicand as well, and we're trying to see if that equals 2. So here we have the square root of 6 plus 10, which is 16, minus the square root of 2 times 2, which is 4. We're trying to see if that difference is 2. Square root of 16 is of course 4, and the square root of 4 is 2. And we want to know if 4 minus 2 is 2, and of course 4 minus 2 is 2, so we get 2 equals 2. So that made it true as well. So 2 also satisfies the original equation and therefore is a solution. So now we can write our solution set containing 18 and 2. So again, the order doesn't matter, but I usually like to write them in ascending order just for reasons of simplicity, and so that all our answers look the same if we agree to all do that. Okay, so this is a pretty significant problem, probably the most challenging one we've done. Notice it is not difficult, but you do have to be careful when you square these expressions which have more than one term in them. We don't want to say binomial. That's actually a term we reserve for polynomials. So we just say an expression with 2 terms in it. And otherwise that should be all there is to it. So go ahead and make sure you can do this on your own before you proceed to the next problem. All right, so here's another one very similar to that one. Since some students tend to have a difficult time with these, I decided we should probably do 2 of them. So by all means, try to do it on your own first and then come back to see if your answer and mine agree. So assuming you're back from trying it, we're gonna go ahead and keep one radical on the left side, like the square root of v plus 7, and we'll go ahead and move the other one to the other side, which changes sign, becomes positive square root of 2v plus 7. And now we're ready to go ahead and square both sides. And when we do, on the left side we get v plus 7. On the right side, we want to be very careful to handle this properly. You can use the formula we just used, or let's switch it up and use the table this time. So we have 1 plus square root of 2v plus 7, 1 plus square root of 2v plus 7. We make a table and multiply it out just like a times table. So 1 times 1 gives us 1. 1 times positive square root of 2v plus 7 is just positive square root of 2v plus 7. Again, 1 times positive square root of 2v plus 7 is positive square root of 2v plus 7. And we know that the square root of any radicand times itself will just give us the radicand. So here we just get 2v plus 7. So we notice now when we want to combine these, the 1 and the 7 can combine. So when we go to write our answer, we also realize that those two are like terms. So we're going to end up with 2v plus 8. That's the 2v. The 1 and 7 give us 8. And then two of these expressions. So plus 2 radical 2v plus 7. Notice that we still have a radical left, so we're going to have to square again. So let's go ahead and get everything other than that radical on the other side. So we have v. Let me bring the 2v over right next to it. So minus 2v plus 7. Let me bring the 8 next to that. So it becomes minus 8. And on this side, we have 2 radical 2v plus 7. So now on the left side, we have negative v minus 1. On the right side, we have 2 radical 2v plus 7. As you noticed, we're ready to go ahead and square both sides again. All right. So here we're going with tables this time, so let's do that. So we have negative v minus 1, negative v minus 1. So notice we end up with positive v squared, positive v, and here when you multiply these again, you get positive v, and when you multiply those, you get positive 1. So notice they all became positive. So we get v squared, and we combine these two to get 2v. Plus 1. And on the right side, we have 4 times 2v plus 7, correct? So just so you know, sometimes what we can do is multiply both sides by negative 1, so this becomes v plus 1, and we just end up with a negative on the 2, which some people find easier to work with, but I like you to be comfortable with negatives. That's why I went ahead and handled it with negatives. So we get v squared plus 2v plus 1 equals 8v plus 28. It's a quadratic, so we'll move everything to the left side. So we get v squared plus 2v minus 8v plus 1 minus 28 equals 0. So we get v squared minus 6v minus 27 equals 0. Now we need to factor that, and I think you find that that's a very easy factoring problem, because we have two numbers whose product is negative 27 and whose sum is negative 6. I don't think you need a factorization table to realize these need to be negative 9 and positive 3. Notice that when you multiply those, you get negative 27. When you add those, you get negative 6. So we get v minus 9 times v plus 3 is equal to 0. So v minus 9 equals 0, or v plus 3 equals 0. That's by the zero factor property. So we end up with v equals 9, or v equals negative 3. So now we're going to go ahead and check 9. So we plug in 9 for v in the original equation, and we end up with the square root of 9 plus 7 minus the square root of 2 times 9 plus 7, and we're trying to see if that difference is 1. So that's the square root of 16 minus the square root of 18 plus 7 is 25. And we want to know if that's equal to 1. So that's 4 minus 5. We want to know if that equals 1. And of course, negative 1 equals 1 is a contradiction. So that's false. So 9 did not make the original equation true, so it's not a solution. You can see how important it is to check these. Now we're going to go ahead and plug in negative 3. So we have square root of, in the original equation, negative 3 plus 7 minus the square root of 2 times negative 3 plus 7. We want to know if that equals 1. Now, that first square root gives us square root of 4 minus, in the next one, we have negative 6 plus 7, which is 1. So minus the square root of 1, we're trying to see if that difference equals 1. This time the square root of 4 is 2, and the square root of 1 is 1. And we want to know if 2 minus 1 is 1. And of course, 2 minus 1 is 1. So we get 1 equals 1. That time it becomes true. So our solution set is going to contain only one number in it, and that's going to be v equals negative 3. So we won't put the v equals, we'll just put negative 3 in our solution set. So be extremely careful to make sure to check, otherwise it's very unfortunate to go through all that hard work and not get the correct answer. So again, make sure that you can do this on your own before we proceed. All right, so that's pretty much as challenging a one as you're going to see with square roots. Just wanted to take a look at a couple of problems with some higher level roots. Here are some cube root problems, and of course we handle them in exactly the same way, except since we're trying to get rid of a cube root to get to the n, we're going to cube both sides. That's the only difference. So we're going to get the cube root of n cubed equals quantity negative 5 cubed, and that's going to be n on the left side, and we get equals negative 125. Since we don't run into similar problems that we do with even indexes or indices with odd ones, they're not mandatory check problems, but it's highly recommended that you check anyway. So just to make sure you didn't make some kind of an arithmetic error. So we have the cube root of negative 125, and we want to know if that equals negative 5. And of course, the cube root of negative 125 is negative 5, so we get negative 5 equals negative 5, which works out. Now we write our solution set, and that contains, be careful not to put negative 5, n is the solution, so negative 125. Next problem in the middle, very similar, except notice whenever we have more than one radical, we try to move one to the other side. So let's keep the cube root of 5a plus 4 on the left side, and let's go ahead and move the other one to the right side, and it becomes positive. So we just get the cube root of 2a minus 3. Now we're ready to go ahead and cube both sides. So we end up with a nice simple linear equation. 5a plus 4 equals 2a minus 3. Sometimes you may end up with something more complex, which you'll solve just like the last couple of problems we did, no problem. All right, so 5a minus 2a equals negative 3 minus 4. So we get 3a equals negative 7. Therefore, a equals negative 7/3. So now when we plug into the original equation, we get to check, we get the cube root of 5 times negative 7/3 plus 4 minus the cube root of 2 times negative 7/3 minus 3, and we want to make sure that that difference is 0. So we get the cube root of negative 35 over 3 plus 4. Let me write it as 4 over 1 because we're about to combine fractions, minus the cube root of negative 14 over 3 minus 3. Again, we want to know if that's equal to 0. So on the left side, we're going to go ahead and multiply the 1 by 3 and make sure we do the same to the 4. On the right side, I forgot to throw 1 under that. We'll do it now. So we'll go ahead and multiply by 3 again on both of those items. And so let's see. So for the first radical here, we get the cube root of, that's negative 35 plus 12. So negative 23 over 3 minus the cube root of, here we have negative 14 minus 9, which is also negative 23 over 3. We want to know if that's equal to 0. No need to worry about figuring out these rather difficult cube roots. Neither one of these is a perfect cube, but we don't need to, because look, we have some number minus itself. So of course that's 0. So we get 0 equals 0. So we made it true. Therefore, negative 7/3 was indeed a solution of that equation. So we get S equals the set containing negative 7/3, just like that. All right, for the last one on the right on this screen, we have a fifth root. So of course, we know that we're gonna have to raise both sides to the power of 5 to liberate that 4x from the imprisonment of that radical. So we get negative 2 to the power of 5. And of course, the fifth root of 4x to the power of 5 is just going to be 4x. And we know that negative 2 to the power of 5 is negative 32. So we get x equals negative 8. If we want to check it, it's actually not that bad, because we have the fifth root of 4 times negative 8. We want to know if that equals to negative 2. And here we have the fifth root of negative 32. We want to make sure that's negative 2. And as you know, the fifth root of negative 32, which is the number you have to raise to the power of 5 to get negative 32, is indeed negative 2. So we get negative 2 equals negative 2. So it made it true. Therefore, it is a solution. So we're going to write our solution set. And that's the set containing negative 8. And that's how you do those higher roots. You just raise to different powers. The power that we need depends on the index. Whatever the index is, we raise both sides to that power. Here it was 5, we raised both sides to the power of 5. Here, where the index was 3, we raised both sides to the power of 3. In the previous problems on the previous screens, we squared because the index was 2. So make sure you understand these simple problems before we proceed. All right, so on the left here, we have a fourth root problem. So here, checking is going to be mandatory because it's an even index, but it's rather simple in the sense that we're ready to go ahead and raise both sides to the power of 4. So we go ahead and proceed with that. We take the fourth root of k squared plus 16k plus 1 and 3. We raise both of them to the power of 4. Notice I always leave the original equation alone because when I want to go back and check, I don't want to mistakenly check a modified equation. So we know the fourth root of any radicand to the power of 4 is just the radicand. So we get k squared plus 16k plus 1 on the left side. And on the right side, we know 3 to the 4 is 81. So now that's just a simple quadratic, which we know how to solve. We'll go ahead and bring the 81 to the left side. So we get k squared plus 16k plus 1 minus 81 equals 0. So k squared plus 16k minus 80 equals 0. Lead coefficient here is 1, so that means we can use the big X. We're looking for two numbers whose product is negative 80 and whose sum is positive 16. If that lead coefficient is not 1, don't use this trick. Go ahead and just open two sets of parentheses and do trial and error till the FOIL requirement checks out, meaning first times first gives you first, last times last gives you last, and the inner product and the outer product give you the middle term. But since it is 1, we'll go ahead and use this. So if you don't see what those numbers are, you can always do the prime factorization of 80 to get this 210, 2551. We see we have, for example, 2 times 40. That's not going to work because it's hard to get 16 out of 2 and 40. 4 times 20 should work, right? 4, this gives you 4, and this gives you 20. So that's the magic combination. And of course, we want a positive 16. First of all, we want two numbers whose product is negative, so we know they're going to be different signs. We're going to have a negative number and a positive number. Since we want their sum to be positive, we're going to want the larger of the two to be positive. So we're going to use negative 4 and positive 20. Notice that their product is now negative 80 and their sum is positive 16. So that should be our numbers. So we get k minus 4 times k plus 20 is equal to 0. So we get k minus 4 equals 0 by the 0 factor property, or k plus 20 equals 0. So either k equals 4 or k equals negative 20. Now we're going to check. Let's go ahead and check k equals 4 first. So we're going to the original equation, the fourth root of, we're plugging in 4. So 4 squared is 16 plus 16 times 4 plus 1. We want to know if that equals 3. So the fourth root of, that's 16 plus 64, which is 80, plus 1 is 81. We want to know if that equals 3. And as you know, the fourth root of 81, or the number you need to raise to the power of 4 to get 81, is in fact 3. So we get 3 equals 3. So that made it true. Now we'll go ahead and check negative 20. Plug it into the original equation, which we left untouched. The fourth root of negative 20 squared is going to be positive 400. plus 16 times negative 20 plus 1. We want to know if that equals 3. Now here we have 400 minus 320, which is 80 plus 1. So again, we get the 4th root of 81. We want to know if that equals 3. And of course, we do get 3 equals 3, so that works out as well. So we have two solutions, which we'll go ahead and write in our solution set, namely negative 20 and 4. So very similar to what we did before with square roots, except here we have a 4th root, so we had to raise both sides to the power of 4. And when you check, you have to make sure you're taking 4th roots. Otherwise, not much different. So in this one, we're going to look at a formula. R equals the square root of a over pi, and we're going to solve this for a. And just because we have different letters, it's not going to make it any difference with the ones that just have one letter in them. So we're going to go ahead and square both sides. So now we have r squared equals square root of a over pi squared, which is of course just going to be a over pi. And on this side we have r squared. The fastest way to solve an equation like this for one of the letters is to go ahead and realize I can throw a 1 down here, and then I can go ahead and cross multiply like that. So I get a equals pi r squared. You recognize that? Yes, that's the formula for the area of a circle. And at first, it was solved for the radius of the circle. But once we squared and solved, we ended up with the formula for the area of a circle. And that's how you do that one. So make sure you can do these two problems before we proceed. All right, so we're going to end the day by honoring Albert Einstein by solving this equation for capital E. Very similar to the previous one, we're going to go ahead and square both sides. So we get c squared equals e over m. Once again, you can throw a 1 there and cross multiply, so you get the good old famous E equals mc squared. Now in this equation, E is the potential energy of a given amount of matter, and m is the mass of matter you're dealing with, and c is the speed of light. So that's a very large number because the speed of light is the fastest speed in the universe. So it's actually 3 times 10 to the 8 meters per second. So that's a 3 with 8 zeros in front of it, meters per second. And a meter is approximately a yard. So imagine something moving at 300 million of those yards almost in 1 second. So that's why when you square that, you get an even much larger number. And then you're going to multiply that by the mass to get the potential energy. That's why so much energy is contained in the smallest amount of mass that you can imagine. And the person who came up with that was, of course, Albert Einstein. All right, so that should wrap it up for the day. And make sure you practice these and be safe until we meet next time.